Okay, welcome back. And now we are going to discuss Euler's proof, part 2. When last we met, our hero, Euler, had gotten this far. He had determined that E, which is equal to the limit as n goes to infinity of 1 plus 1 over n to the n, can be represented as an infinite series of reciprocals of factorials. Okay? Today we want to look at the question, what happens when we've got e to the x? So before we can jump into this, we're going to have to do a little bit of limit work, which is going to be a little bit painful, but I think we can make our way through it. Let's start with this. E to the x, according to Euler's definition, would be equal to the limit as n goes to infinity of 1 plus 1 over n to the n raised to the x power, which we could simply represent as the limit as n goes to infinity of 1 plus 1 over n, and then using the rules of exponents to the n times x. Okay? Now, the problem here is that we would really like to deal with this issue somehow. All right? And it's not quite clear how to accomplish that. So, for starters, why don't we do a little substitution, and let's let m equal n times x. Okay? We'll let m equal n times x. So first of all, n is going to infinity. What's going to happen to m when n goes to infinity? Now, we're accustomed to thinking of x as a variable, but don't think of x as a variable in this case, because x is just some value that we're going to put up here in the exponent. Maybe it's e squared. Maybe it's e to the pi. But whatever it is, it's not going to change. All right? Think of x as fixed. It's a number. And when we take that number and multiply it by something that's going to infinity, it's going to go towards infinity. So if n is going towards infinity, m is going towards infinity also. Okay? One other thing I want to do, not to insult anyone's intelligence here, but if m is equal to n times x, that means that n is equal to m over x. And the reason that's important is that I'm now going to take this limit and rewrite it in the following way. I'm going to say that e to the x is equal to the limit, and now I'm going to let m go to infinity. Because we said if n is getting bigger, m is getting bigger. Okay? This is still 1, but now where I have 1 over n, I'm going to write that as 1 over m over x, which is actually x over m. Right? And where I have n to the x, I'm going to represent that as just m. Okay, well now that is an interesting result. Right? What we're saying then is that as if you have e to the x, that's equal to the limit as m goes to infinity of 1 plus x over m to the m, which looks just like the definition of e, except that you've got an x in this numerator. All right? So let's keep that result in mind. In fact, I'm going to reproduce it right here. E to the x equals the limit as m goes to infinity of 1 plus x over m raised to the m. And now let's do exactly the same thing that we did yesterday. You know, let's just think of these as n's so it doesn't confuse us. It's all the same thing. All right, we're going to do the same thing we did yesterday with a binomial expansion, except this time we've got this x. So let's think back to yesterday. What did that look like? We had the combination of n things taken 0 at a time times 1 to the n power times, and yesterday we had 1 over n, but today we are going to have x over n to the 0. Let's write some more terms. N things taken 1 at a time times 1 to the n minus 1 power times x over n to the 1 plus a combination of n things taken 2 at a time times 1 to the n minus 2 times x over n squared plus, I think we can squeeze in one more here, a combination of n things taken 3 at a time times 1 to the n minus 3 times x over n cubed, etc. Okay, so what's that going to look like when we expand it? Well, it's pretty much going to look like what it looked like yesterday. First of all, I'm not going to deal with all these 1s to the n's, because that's just 1, right? So just dealing with the combinations and the x's, okay? So this was just 1 times, and now x over n to the 0 is still going to be 1. So that's easy. This is going to be n times, and this is going to be x over n. This, just like yesterday, nc2 is going to end up giving us n times n minus 1 over 2 factorial. And whereas yesterday we had a 1 over n squared, today we are going to have an x squared over n squared. Okay. nc3 is going to be n times n minus 1 times n minus 2 over 3 factorial. And now we're going to have an x cubed over n cubed. And let's squeeze in one more here. N times n minus 1 times n minus 2 times n minus 3 over 4 factorial times x to the 4th over n to the 4th. And now, just like yesterday, okay, we can just write this as 1, I think. We have a bunch of limits. Here, clearly, the n's cancel, and we're going to get an x. Here, the largest term, because this is all, again, a limit as n or m, whatever is going to infinity. This leading term is n squared. This is n squared. That's going to cancel, and we're going to get x squared over 2 factorial. And then here we're going to get n cubed, and we'll just have x cubed over 3 factorial. And here we'll have x to the 4th over 4 factorial, etc. And we can now generalize and say that e to the x is equal to the limit as n goes to infinity of 1 plus x over n to the n, which is equal to the summation as n equals 0 to the infinity of, and now instead of 1 over n factorial, it is in fact x over x to the n over n factorial. All right, does that make sense? Let's see, when n is 0, we've got x to the 0, which is 1 over 0 factorial, which is 1. When n is 1, we've got x to the 1 over 1 factorial, which is x. When x is 2, we've got x squared over 2 factorial, x cubed over 3 factorial, etc., etc., etc. Okay, very interesting result. So now, let's just write this down again here. E to the x equals the summation n equals 0 to infinity of x to the n over n factorial. So then what about something like 1 over e? That would be equal to e to the negative 1. So now x is negative 1, which means we're going to have negative 1 to the 0 over 0 factorial plus negative 1 to the 1 over 1 factorial plus negative 1 squared over 2 factorial plus negative 1 cubed over 3 factorial plus negative 1 to the 4th over 4 factorial. Well, what does that equal? That equals 1, we'll say 1 over 0 factorial, minus 1 over 1 factorial, plus 1 over 2 factorial, minus 1 over 3 factorial, plus 1 over 4 factorial, etc. Well, that's pretty cool. Remember, yesterday we said that E was equal to something that looked like this, except all pluses. So how weird is that? You go back to the series that is E, flip the sign of every other term, and you get 1 over E. Pretty weird. What about E squared? That would be equal to 2 to the 0 over 0 factorial, plus 2 to the 1 over 1 factorial, plus 2 squared over 2 factorial, plus 2 cubed over 3 factorial, plus 2 to the 4th over 4 factorial, which would be, again, 1 over 0 factorial, plus 2 over 2 factorial, plus 4, hey, that's a 1, just kidding, plus 4 over 2 factorial, plus 8 over 3 factorial, plus 16 over 4 factorial, etc. So the numerators are increasing as, in this case, powers of 2, and the denominators, once again, are the factorials. And if you wanted something like 1 over E squared, we would do the same thing here. We would just flip the signs of every other term and make them negatives. All right, I think that's enough for part 2.